they're saying if you have, oh, maybe, so anytime you have, your B over there on the right hand side of your equation is all zeros, that's a homogeneous. And they're saying that it always has one solution, and that's a trivial solution, which is all your x's, your x1 through x something, are all zeros. So it always has that solution, and that's called the trivial solution. Now, if it has any solution other than the trivial, it's non-trivial, and notice on the next page, 44, it says, homogeneous equation AX equals 0 has a non-trivial solution if and only if the equation has at least one free variable. So, if you go through your matrix and you go down and you get a row of zeros, then you have a free variable, and then it has a non-trivial solution. But if you go trying to solve, to do an echelon form or a reduced echelon form, and you have no rows that are zero, then it has only the trivial solution. So that's what it's telling you there. And then when it has a row of zeros, then you can get parametric form for your x1 through x, whatever your x's are. You can get it parametric form, and then what you can do is you can write that thing in vector. You'll solve when you have a non-trivial solution and you have a free variable, then you solve it for parametric, and then what you do is you solve for x1, x2, x3, x4, whatever it is, and then you can write that solution out in parametric form, and you can then get it so that you have weighted values of that parametric form, and probably it becomes apparent when we do some problems. Now, when you have it in parametric form, they're going to talk on page 45 and 46. If you have a vector column, that doesn't have a x weight, what that's doing is, and they're showing you there, it's moving the solution plane up parallel to the existing plane that the matrix A spans. So that's what they're talking about on 46. And then theorem 6, where it says, suppose the equation AX equal B is consistent for some given B, and let P be a solution. So if it's consistent, then what you have is you don't have any rows that are zeros. You actually have a solution, and then you can. Then the solution set AX equal B is a set of all vectors of the form P plus V0, and then it's saying that what that is it's the homogeneous solution and it moves it up and down parallel to that homogeneous solution. So down there in the middle of 47, writing a solution set of a consistent system in parametric form. It says we'll reduce the augmented matrix to the reduced echelon form, express each basic variable in terms of any free variables appearing in the equation. Write a typical solution x as a vector whose entries depend on the free variables, if any. Decompose x into linear combinations of vectors with numeric entries. We'll look at some of those problems. Okay. And on page 48, section 1.5. Number 2, and it says, in these exercises, I'm just reading the instructions, determine if the system has a non-trivial solution. Try to use as few row operations as possible. So number 2, so this is going to turn out to be a homogeneous type, and we want to know if the only solution is the trivial solution. So our augmented matrix would be and then we're just going to go through the process of reduced echelon and reduced echelon if we have to get that far. So I got to multiply 2 times the first. Minus probably the easiest thing to do there. Is divide that second rule by -5. That's what I'm going to do. I've already done something. Now, we can see there are no free variables, right? Because there's no rows that are zero. And therefore, only trivial solution. Say, then it would have a free variable. Then it would have a non-trivial solution. But as long as it does not have a row of zeros, if there's, then it's going to, the only thing it has is the trivial solution. Now the next one, now you see, if we tried to make an augmented matrix, we would automatically have what? We would have to have to make it fit, we would automatically have to have that. We would have to have that row of all zeros to get x1, x2, x3. And so what do we have? Then we'd have a free variable on, and what it would be would depend upon, I should probably do the rest of this. To find out what it is, you would, let's just finish this thing out. I'm going to switch rows. And I'm doing this just to show you that, we don't have just one, we don't have two. And we'd have to multiply the first row by 5 and it. Now, you see x1 and x2, we would have solutions, but x3 would be free, and we'd have to be writing parametric equations for x3, because our solution would all depend upon x3. We'd want it, but they're asking only if the trivial solution is the only one, and the answer is no. There are non-trivials. Now, there's an infinite number of non-trivial solutions, because it would be whatever you would pick x3 to be would give you a different parametric result. So 5 and 6 it says follow the method in exercises 1 and 2. Write the solution set as of the given homogeneous system in parametric vector form. It's so much nicer having this. 6. So you want to get this to reduced echelon form. What you're doing is you're just following the instructions on page 47. This is writing solution set. 1. So this has what? Non-trivial solutions, right? So now what we do is we have to write this in parametric form. So that this first line right here says that x1 plus 3x2 minus 5x3 equals 0. And then the second line says x2 minus 3x3 equals 0, and x3 is free. Right? Can be whatever you want. You assign the value. So then we're going to take this first equation and solve it for x1. We're going to solve the second equation for x2. And x3 is free. So now what we're going to do is our solutions, x1, x2, x3, that vector is going to be I take this value right here and put it up here. X1 is a minus 3x2 plus 5x3. And then I put this one for x2 minus 3x3. And then I put x3 because it's free. It can be whatever it wants. Okay. What's that? Did I do something? Oh, thanks. Thanks. Now, when I'm going to write this, I'm going to write these as vectors. So, I'm going to put all the x2s together, and there's only one x2 minus 3x2 0 0. See, there's there's 0 times x2 plus 3x3. And then this one here, there's 0 x2s, and then x3 is 3. Plus 5x3, 3x3, x3. Do you see what I did? Just put. Now then, this is times x2. So if I take x2 out of this vector, I take x3 out. And you see it, it says, I've done what it asks me to do. I've done if I did it right. Rats. It didn't go far enough. I didn't get this matrix all the way reduced. I could have taken this thing out. Do you see that? For me to erase it and okay. You didn't tell me, you didn't remind me. If you think there's an error, you should say. But I'm going to go back and I'm going to eliminate that. Let's not erase that. Let's leave the mistake there. And tell me what it is. We'll do it over here. We'll do it correctly.
Matrix with this.
Yeah, that one with the 3 in it. One, what was it? One.
Matrix is 1, 0.
Well, no, do it 1, 3.
Oh, 1, 3. The next row is 0, 1, 1, 3, 0, 1, 0, 2, 6.
Okay, I actually want just that. This one right here. This one with the 0 row right here. So we'll just go back and put zeros in there. Okay. Do you see what I did wrong? I could have eliminated that 3. Should have eliminated that 3. And so, if I do eliminate it, then it becomes 1, 0, and I'm multiplying -3 times the second row. So that makes this a 4, 0, 0, 1, minus 3, 0, and then 0, 0. Because you want to go as close as you can to reduced echelon form. Sorry. You see, everyone see my error? Now then, let's do the parametric. This one says x, the first equation would be what? x1 plus 4x3, right? The second one is x2 minus 3x3. And then x3 is free. And solve this one for x1. This one for x2. And then this one is free. Then you go to your solution vector. And then you replace the x1 with a minus 4x3. And the x2, you replace it with 3x3. And then x3 is 3. So then you factor the x3 out. No. So your weight will be whatever you pick x3 to be, times that vector. All right. That's the way they want you to do it. Okay. Now, 7 through 14 says describe all solutions of AX equals 0 in parametric vector form where A is row equivalent to the given matrix. 8. Now, what this is doing, this is saying that this is the A matrix. So technically, it has 2 rows that are zeros. It has 2 free variables. Because it has x1, x2, x3, x4. So technically this thing should be this way. And then it's a homogeneous type. So you have your value, it's AX equals 0. That's what they're telling you. So you have a row of zeros out here, and then you got 0, 0, 0, 0, 0, and 0, 0, 0, 0, 0. So at this point, you got 2 free variables. Now, whether you have the third one or not depends upon when you try to reduce it to reduced row echelon. So you got turning points in the first 2, and what you want to do is you can still eliminate this one right here, right? So that's what we want to do. So we go 1, 0, and I'm multiplying the bottom row by 2 and adding it up, so it's minus 5. That's now you don't have to put that last column up there, zeros, but I just you don't have to put these bottom ones, but to me it helps that you recognize what the heck you're dealing with. So, and now I've got this thing as much reduction as I can get, and I got 1s in my diagonal row, right? My turning positions. So now I'm ready to write it in parametric form. So the first equation says what? X1 minus 5 x3 minus 7x4 equals 0. And the second one says x2 plus 2x3 minus 6x4 equals 0. And then x3, 3, and x4. Then I want to solve this for x. First one for x1. Second one for x2. X3 is 3. X4 is 3. So now my solution vector Now, if it helps you to do it, what you can do is write these as column vectors this way. You can skip this step. What I'm doing is I'm breaking this thing down into its column things over here. So my weights x3 is 5 minus 2, 1, and 0 plus x4 weight 7, 6, 0, and 1. Sometimes for me, what it does is it just helps to break it down as much as I can so that I don't mess it up. And I still mess it up, right? When you teach, you make a mistake, you make it in front of a whole class. All right, any questions on that? Do you understand it? Let's just take a practice shot at at 10. You kind of tell me how. It's 1, 3, 0, minus 4, 2, 6, 0, minus 8. Right. Does it help if you put the column of zeros out there and the 2 rows of zeros for you to kind of visualize? I mean, because this, you understand, this is just the A matrix. I'm gonna put when you guys don't say anything, you don't give me much feedback here. And then when you say I'm wrong after I finish the problem, it's negative feedback, right? So first thing I want to do is that first column, I want to get rid of that 2 in the second row. So I'm going to subtract 2, multiply by 2, subtract 2. So what just happened to that second row? It went free on me too, didn't it? Right? So I got x2 is free, x3 is free, x4 is 3. And I got one parametric equation which says x1 plus 3x2 minus 4x4 equals 0, correct? So then I'll solve that for x1, negative 3x2 plus 4x3, and then x2 free, x3, x4. Wait, what's your question, Ashley? Oh, this is x4. Thanks. Thanks. Thanks for asking the question. Does that make more sense? Okay. So now, this is my solution vector. So my x1, I'm going to put a negative 3x2 and then 4x4. Then I'm going to have an x2, right? Then I'm going to have an x3, and I'm going to have an x4. Now, the reason I set this up right here is so that I can see that this is 0x3, right? And this is 0x3, 0x4. Rather than just write all of that thing in a jumbled deal, then I can kind of see what my vectors when I pull my weight of x2, x3, right? Otherwise, I've gotten, I get confused on what or else I miss it. I miss enough stuff. 3, 1, 0, 0. And then it's x3, and that's 0, 0, 1, 0. x4, 0, 0, 0. I think this is supposed to be a 4 up here at the top. It's underneath my hidden successfully. See, because it's right up here. So that should be my solution vector in parametric form. It's cold in here, isn't it? Yeah. That's just not me. What? I'm cold underneath my sweater. 14 says, suppose the solution set of a certain system of linear equations can be described as x1 equals 3x4, x2 equals 8 plus x4, x3 is 2 minus 5x4 with x4 free. Use the vectors to describe this set as a line in X4. So they're essentially telling you all of these different values. So they've got X1 equals 3X4, X2 equals 8, so they solved it for parametric, right? These are the parametric. And it says X4 is free. And then they just want it in this vector form. So my solution thing, this is 3X4. So we have this constant vector 0, 8, 2, 0. And then we have this x plus x weight vector 3, 1. But that's what we have. It's asking us a little, it says, describe the solutions of the following systems of parametric vector form, provide a geometric comparison to the solutions in exercise 6. So, to get the solution, we have to do reduced row echelon form. That's taking a minus 1 times it. Get 3 times it. Did I do that right, or have I got an error in it?
I think this 10 on the last row is supposed to be bigger, so.
This, oh, this is supposed to be -7. That's what you're saying. That would help. So I'm taking 3 times 3 is 9. That makes this thing true. Now, does that look better? Look pretty bad. 1. And then I'm multiply -2. Do something else wrong? Oh. Hate it when I can't subtract. When I multiply 3 times 4 is 12, and I subtract 6, I don't get it. I get 6, not 5. Now, I got a free variable x3, but I want to eliminate this 3 right here before I go to parametric form. See what I'm doing. Is that a -13? That don't seem right. What's that? Well, this is supposed to be, oh yeah, there we go. So then, now then that would be a -5, right? Ooh. Now what I want to do is I want to get in parametric form because I got it reduced as much as possible. And this thing has that row of zeros out there. No. This thing is this one. This is x1 plus 4x3 equals -5. x2 minus 3x3 equals 3. And then x3 is free. So x1. Yeah, I can see that. Thank you. Must be getting close to the end of the class period. X2 equals, I better finish this. X1 is 4, X3 minus 5. This one is minus 3x3 plus 3. X3 is 4. So So they want us to compare that with the solution in 6. Did I do something?
Yeah, for the X3 vector, should it be positive? That's the reasons for having it.
Oh, yeah. I'm gonna quit. Okay. That's at 6. There's 6. I can't even, at this point in class, I can't even think. Is the X3 vector minus 4, 3, 1? Is that the same as this one? No, it's not. I might have did this one wrong. I think what they were trying to do is that 6 should have this vector the same without a constant, and then this vector would have switched that plane that vector was in out to that new point. Did we do 6 right? We can't compare it because there's no comparison to be made. Well, I think we'll quit on that fairly negative note, and I'm going to go I'm going to skip that application section and we'll go over to independence. Now, if you recall back when you were doing problems, in order to have a unique solution, they had to be consistent and independent. A consistent set of equations says it has at least one solution. An independent says it has at most one. And if they're consistent independent, they have one. At least one, most one. If they're both, they have one. And we've been dealing with a consistent set of equations, and we have seen that non-consistent equations are ones that have free variables and it's written in parametric form, so you have many solutions. So they're consistent because they have at least one, but they have many solutions. Now we're going to talk about they have to be independent, and that means they have to have at most one. And so if they're consistent, have many, independent, they have at most one, then they have one solution. And that's what you want, because you want systems of equations that are consistent and independent. Dependent equations are like, if you think about two-dimension, dependent are lines that lay on top of themselves. They dependent. They're just multiples of each other. So you have many solutions. You have an infinite number of them. So that's what we'll do is we'll start linear independence then on Tuesday.